Hello students, welcome to the EN 401 lecture on moment of inertia. Here's the roadmap for our moment of inertia lecture. We're going to talk about the basics, and then we're going to talk about how we calculate the moment of inertia for simple shapes. We'll talk about the parallel axis theorem and what that means, and then move on to complex shapes with the table method, and then we'll specifically talk about moment of inertia for I-beams. So what is the moment of inertia? Essentially, the moment of inertia is a measure of geometric stiffness for structural members. Essentially, structural members with high moments of inertia are going to be geometrically stiffer and stronger than those with lower moments of inertia. And that assumption goes if it's the same material and the same cross-sectional area. So the importance of moment of inertia is we really want to optimize our moment of inertia so that way we can increase the strength to weight and cost ratio for our structural members. Essentially, we could make anything as strong as we need it to be, but as engineers, we want to do that effectively. Right? We don't want to use material in our structural members that don't really serve any purpose or don't really add any additional strength, but make the members more heavy and expensive. So down here in the bottom we have some pictures of some steel structural members, and you'll notice that first of all we have this I-beam here, right? We'll learn why I-beams are used a lot in steel construction. Essentially, they take advantage of the principles of moment of inertia, so we can use a little bit of material and get a lot of strength. Additionally, like we have all these structural members here, and you'll notice that all of them are hollow, right? So what we'll find with moment of inertia is that if we made them solid, sure, it would add strength, but it doesn't really add as much strength as making the structure member thin-walled and really increasing our moment of inertia. Go ahead and watch this video here at this YouTube link. It's kind of a fun video. It shows how by just increasing the moment of inertia of some materials, you can get a really strong, interesting I-beam. So go ahead and pause and watch that video here. Alright, so we know that moment of inertia is essentially a measure of geometric stiffness, but what it really is the measure of distribution or variance of area about an axis. Right, so moment of inertia is going to tell us how much area is distributed away from an axis. Right, so our first bullet here, if the area is bunched up about an axis, the moment of inertia will be small. So let's take a look at this example here. Right, we've got this kind of thin little member here, and this is our x-axis, central x-axis running through the middle. And sure, this might have a decent amount of area, but all the area is really bunched up close to that x-axis, right? So the moment of inertia of this shape about its central x-axis would be small because the distribution of area away from that axis is also pretty small. It's all bunched up pretty close. So a great example of this, easy thing for you to do at home or wherever you're at right now, is go ahead and grab a paper folder, right, and hold that paper folder out in front of you, sort of in the same orientation as this example here, and notice that when you just hold it from the very end, one end of it, and you'll notice that it bends pretty easily, right? It's pretty floppy. You can't really stop it from bending up or down. That's essentially because it's not very stiff, because all the area in that folder is all bunched up about that x-axis there. All right, so the second ball here, so if the area is spread out, we're going to get a really large moment of inertia. So that holds for this case here. So same structural member, or same member, but now we're going to examine the y-axis, and we can see that about the y-axis we have a lot of area that's spread far away from the y-axis, right? So our x-axis, everything's real close, right? Everything's just real close to the x-axis, but for a moment of inertia about our y-axis, everything's spread really far. And we know if we have a large, if it's spread really far, we'll have a large moment of inertia. And if we have a large moment of inertia, we know that our object will be relatively stiff. So we can prove that if you take that folder and instead of holding it like we have here, turn it sideways. So turn it 90 degrees, this way, and then try to bend it in that same up and down fashion, right? You'll see that it won't bend up and down if you turn it 90 degrees. You could bend it, side to side, but it won't bend up and down, right? Because now we're trying to bend it about this y-axis, and essentially that's not going to happen. So we can see that a shape will almost always have different values for the moment of inertia, or the ix about its x-axis, or the moment of inertia about its y-axis, or iy, right? So not every direction in our shapes or our objects is the moment of inertia going to be the same. So it all depends on the axis orientation. Units for moment of inertia are going to be length to the fourth. Still, we'll probably see a lot of inches to the fourth for our moment of inertia calculations. And then, finally, let's take a look at one other thing, one other example here. So we have this example here. So it's a rectangular, thin-walled, potentially structural member. And we can see that, all of our area is pretty far away from the x-axis, right? And pretty far away from the y-axis. So our thin-walled shapes here would end up with a pretty high moment of inertia. And we can also see that, putting area in this middle area here, it's not going to add a lot of area away from our axes. So we see that the middle area doesn't add a lot of stiffness, geometric stiffness, to our object. So how do we calculate the moment of inertia? Well, we would do some integration, which ends up being a pretty tough calculation. But with the integration, you could potentially solve moment of inertia of any shape. If you're really interested in the integration, go ahead and watch this video here. Luckily for us, someone's done this integration, hundreds of times, and they have come up with predetermined values for moment of inertia for simple shapes. And the key here is these predetermined values are about each shape's own centroidal axis. So the table on next slide is going to show us some predetermined values for moment inertia for some simple shapes about their own centroidal axis. So this chart here shows how you calculate the moment of inertia about the centroidal axes for some simple shapes. For the most part, we'll be dealing with a lot of rectangles. So you should definitely memorize these equations. So the moment of inertia about the x-axis for a rectangle is going to be 1/12 bh cubed, or bh cubed over 12, right? And remember we said that moment of inertia is in length to the fourth. So we have length to the fourth in the numerator here, so we end up with length to the fourth as our moment of inertia value. The moment of inertia for a rectangle about its y-axis is hb cubed over 12. So you just flip the b and the h, which seems to make sense to me. Here's triangle, gives you Ix bar, and then here's a circle. Ix bar and Iy bar are obviously the same because a circle is symmetrical about its x and y axis. So there's those equations there. So now that we know how to calculate the moment of inertia for simple shapes about their own centroidal axis, now we're going to get into calculating the moment of inertia of a shape about another axis that is not its own centroidal axis. All right, so to do that, we use what's called the parallel axis theorem. Right, and the parallel axis theorem tells us that we can calculate the moment of inertia about another axis that's parallel to our centroidal axis, right? So in this big shape here, we have our centroidal x-axis, and we can use the parallel axis theorem to calculate the moment of inertia of this shape, this big blob shape, around this parallel x-axis here. And we'll see why we need to do that in the next few slides. So the equation for parallel axis theorem is Ix, so the moment of inertia about the x-axis, so that would be this x-axis here, is equal to Ix bar. So Ix bar is the moment of inertia of a shape about its own centroidal axis. So that would be the moment of inertia of the shape about its own centroidal axis. If this were a rectangle, that would be BH cubed over 12. That would go in there. And then the next piece of our parallel axis theorem equation is Ix bar plus AD squared. So A is just the area of the shape. And then D, this is probably the most difficult piece of this, is the perpendicular distance between our centroidal axis and our new reference axis. So that perpendicular distance. So if we're doing the moment of inertia about an x-axis, this distance would be a distance along, the y-axis here. And if we're doing Iy, then like in this case here, so here's our centroidal y-axis. If we wanted to find Iy about that axis there, our distance would be that distance, which you see is along the x-axis. The reason that the parallel axis theorem is important is the parallel axis theorem allows us to calculate the moment of inertia for complex shapes, right? So, combinations of other simple shapes. So here's our six-step process to calculate the moment of inertia of a complex shape. So essentially, steps 1 through 3 we've seen before is find the centroid of the overall shape and making sure that you don't skip locating the centroid of each shape. Right, so we've already seen this before. So you want to find the centroid of the overall shape. Step 4, a little bit difficult part of the process. You need to calculate the distance from the centroid of each shape to the overall centroid. Right, so we'll just do a quick little sketch here. So if we have this T-shaped object, right, and here's the centroid of the top piece, and here's the centroid of the bottom piece, and then the overall centroid ends up being somewhere in here. There's our overall centroid. Then we need to find what these distances are. We need those distances. Right, once we have those distances, we can then use the parallel axis theorem to calculate the Ix, the moment of inertia, about our overall centroidal axis for each shape. And then step 6, we go ahead and sum those up. Right, so remember, part of the finding the centroid process is calculating the area, so you'll already have that. So I think the easiest way to do these complex moment of inertias problems is to use a table, which is on the next. So here's our table to calculate the moment of inertia. All right, so our first three boxes here. This is for the centroid. Right, so we got to find the centroid of the shape. So this table here just has x, but you could also add in columns if you wanted to, do your y-axis also. Right, so we're looking for the centroid of the overall shape. We get that done. And then we're going to calculate the moment of inertia for each shape about its own centroidal axis, right? So that's our Ix bar. So this might be, BH cubed over 12 if it's a rectangle. Right, so we do both of those. Then we need our distance. Remember, so this distance, I think it's where most students get confused. This distance is not equal to xi. So it is not equal to xi. Xi is, from an arbitrary plane, so you can find the centroid. Remember, our distance is from the centroid of each individual shape to the centroid of the overall shape. So you can actually calculate d by taking x bar minus the xi should give you that d value there. And then once you have the d value, you go ahead and solve for the moment of inertia using the parallel axis theorem about the overall centroidal axis. So Ix equals Ix bar plus a, which you have here, and d squared. So make sure you square this value over there. And then once you have both of those values, sum those up, and you get your final answer there. So we typically use in this class that table and the parallel axis theorem to calculate the moment of inertia of I-beams. Right, and so why are I-beams great as structural numbers? Well, they take advantage of the parallel axis theorem. Specifically, this d squared function. Right, so in an I-beam, let's say this red line here, that's our central x-axis of the entire I-beam. Right, and in I-beams, what we do is we take these large pieces of steel, call these the flanges. Right, we take these big pieces here and we put them far away from our centroidal axis, right? So d is a pretty big number, right? So we increase this d value, which ends up being squared, and that gives us a large value for Ix. So what happens is I-beams end up being very strong about their x-axis, right? So if we load I-beams like this, they end up being very stiff and very good at resisting bending when loaded from the top. I-beams are not quite as strong about their y-axis because all the area, there's no big flange floating over here, right? All the area is, spread a little bit out on the flanges, but not so much in this central section here. We call this central section the web. So we actually have that written here. So the web is what connects the two phalanges, right? And so for the y-axis, right, all of the, that was not a very straight line, but all of the area is bunched up close to the y-axis in the web, so really almost no contribution to y-axis strength, and then all the stiffness would just be from these edges of these flanges here, so not very much. So I-beams are almost always stronger and stiffer about their x-axis than their y-axis because they're designed to take advantage of the parallel axis theorem with regard only to the x-axis and not to the y-axis. So here's example one. So this one wants you to calculate the moment of inertia about this x-axis down here. Right, so you have to use the parallel axis theorem. So you find the moment of inertia about this rectangle's own centroidal axis, which is this axis, right? And then you need to find the area, which should be simple, and then your distance, which in this one's given to you. Right, the distance between these two parallel axes is 9 feet. So go ahead and solve that, and there is an example video also. All right, here is example number 2. So here's an I-beam. Go ahead and solve for the moment of inertia about the centroidal x-axis. All right, luckily for you on this one is symmetrical, so the centroid of the whole thing is pretty easy to find. Makes it an easy example. And here's example 3. We have a rectangular plate with a hole drilled in the middle. So when you do your table method, you can just use this as a negative area. So you just subtract that from the total moment of inertia. All right, and here's the review. Remember that moment of inertia tells us the geometric stiffness of an object. All right, and yes, it does depend on axis orientation, right? So for these simple shapes, we have predetermined equations, so go ahead and use those. The parallel axis theorem, remember that allows us to solve for the moment of inertia of complex shapes. And then, for that moment of inertia of complex shapes, use that table method and the six-step process that we outlined. All right, thanks for watching.